Have you ever looked up at the sky and noticed that there's kind of a line of clouds? We kind of see that in this picture right here, where there's clearly an area where there's a bunch of clouds and then an area of clear sky. Well, that's what we call a storm front, and we're going to learn about that this week. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here. The first thing we need to talk about here to understand this is the idea of air masses. So you can see from this image here the idea that you have some different areas of air, and that's kind of what we mean by air masses, different areas of air that have certain properties to them. So you can see like this area in here is a cold air mass. It's cold air, which kind of makes sense because it's near the poles, right? And you can see some hotter air, some warmer air down in this area here, right? And again, that makes sense. You know that like places like Florida and Texas and stuff like that get really hot because they are near the equator. So all of this kind of makes sense, right? And the idea here is that there are different types of air masses that we can have that have different qualities to them. And basically what we mean is that they have a certain temperature and a certain level of moisture. And if you think about that, they can either be cold or they can be hot, and they can be dry or they can be wet, and then we can get any sort of combination of those things. So you can have a cold and wet air mass, or you can have a warm and wet air mass, and similarly you can have a cold and dry air mass, or you can have a warm and dry air mass. So these are all kind of these different types of air masses, and so we need to learn the names for these. So make sure you fill in your little blocks here as you go. So first of all, we have a maritime polar air mass, or MP for short, and that's going to be cool because it is polar, and it's going to be moist because it is maritime. And you may not know this, but maritime means like the ocean, it means the sea. So that's going to be cold and wet air. Next, we have maritime tropical. And so, again, maritime meaning wet or ocean related, and tropical, I'm sure you guys know that word, and that's going to be warm, and that's going to be an MT air mass. MT for maritime tropical. Next, we could have a continental tropical air mass, which is hot and dry. You might want to write that in there, that part, that it's continental and tropical. And our next air mass is going to be maritime tropical over here. We can get some maritime tropical air mass over here, which of course would again be warm and moist. We can get a maritime polar air mass coming from this area. Maritime polar would be, again, cold, moist. We can get continental polar coming from this area. That would be cold and dry. And finally, we have continental Arctic, which is going to be really cold air. Now, the whole idea of how our weather changes over time, basically on a day-to-day basis, is based on where these air masses are coming from. So the basic idea here is that if we get air that is kind of moving in this direction from northwest to the southeast, and it comes over us here in Virginia, then we're going to get cold, dry air happening. If we have air that is moving kind of from the southwest, we might get warm, dry air. And if we get air that's kind of coming up from the Gulf of Mexico here, we might get some warm, moist air. And so you can see in this animation here how the air is kind of moving along over time. And this should not be a surprise to you. Think back to last week when we talked about the idea of global winds and the idea that due to differences in pressure and the Coriolis effect, for the most part, air tends to move in that direction over the United States. And so we tend to get air moving from kind of the western part of the country or the central part of the country towards us. And there, depending on what's going on, it may come up from a south direction, or it may come from a northerly direction, and things like that, and that will affect the type of weather we have. But a big thing that we need to talk about next here is the idea of, well, what if we get some air coming from the north and some air coming from the south, and they kind of run into each other like what we see right here? Well, if you know anything, if you've ever seen any sort of weather maps on TV when they do the weather and things like that, you may know that this stuff here, well, that's rain, and that's what happens when you get two air masses colliding with each other. The boundary between those two air masses, where they meet up, is what we call a storm front, and as the name implies, this is going to bring some bad weather with it. So, storm fronts are caused by air pressure. They are caused by differences in air pressure. Basically, the idea here is when you get a cold air mass and a warm air mass running into each other, you guys should be able to kind of think this out. So think for a second. What's going to happen when a cold air mass meets a warm air mass? Okay, so what you should be thinking there is the idea that the warm air is going to rise and the cold air is going to sink, right? So basically what happens is the cold air kind of pushes up underneath the warm air and forces it to rise up, and that's how we get storm fronts that are happening. And remember that when we talk about cold air and warm air, this is just relative to each other. We're going to have a warmer air mass and a colder air mass. So it could be an air mass that is 70 degrees versus one that is 50 degrees, or it could be an air mass that is 30 degrees versus one that is 10 degrees. So it's just the difference in temperature. The colder one is going to sink underneath, the warmer one is going to rise. And you guys should know at this point that when warm air rises, the water starts to condense and form clouds. So it makes sense that we would get storms and clouds at these boundaries between warm and cold air. So this is kind of what I was talking about at the very beginning of the video. Like I said, you may have seen before where you look up in the sky and it looks like there's this sort of very clear mark, this very clear line between where the sky is clear and where the sky is cloudy. That's your storm front. And this is all, as I've just said, this is all caused by this idea of convection, cold air sinking and warm air rising. All right, so we're going to have a few different types of fronts here. And before I describe all these, basically what I would like to point out here as far as a way of remembering this is that think of it as whichever one is doing the bullying, doing the pushing around, that's the one that is going to be the name of the front. So in this case, if you look at this little animation here, you can see that it is cold air that's kind of moving in this way and forcing this warmer air to rise up. And what's that right there? That's a cloud, of course, because as the warm air rises, the water starts to condense and form clouds and precipitation. Notice how all of these things that we've learned so far, the idea of the water cycle, the idea of pressure and different temperature air and moisture in the air and even global winds and things like that, is all kind of coming together. All of this knowledge is coming together here. All right, so the cold front, which is the one doing the bullying here, doing the pushing, cold fronts form where cold air moves towards warm air. This creates severe rainstorms. This is your classic thunderstorm at this point. Whenever you have these really severe, quick thunderstorms, that's usually pretty typically a cold front. This is the symbol on a weather map for a cold front. You're going to need to know those, so draw that in your notes. And you can see here, this is a good example of some fronts coming in right here. You can kind of see that boundary right there. But this one is kind of, that one is a little bit more gentle looking. This is a really cool one right here. Very clear kind of front coming in right here. You can see the edge of it right there. Again, you can see this one right here, very clear line here. This is, at this point, you can imagine the idea that over here is cold, sinking air, and it's basically getting up underneath this warm air that's over here, making it rise up here, and as it rises and reaches that point where it reaches the dew point, and the water starts to condense and form clouds. See another one here, this sort of line of clouds coming in here. So, and one right here. Now, this is a good example because we've talked about this idea of land breezes and sea breezes and how the difference in how much the sun heats the earth. So remember, if you were standing here on this beach, the sand over here would feel very hot on your feet on a sunny day, right? And the water would feel kind of cold. So in this area, but over here we have another beach over here, right? All right, so we have cold air over here. We have warm air over here, which is being forced to rise up and form precipitation because, of course, that warm air has a lot of moisture in it because it's near the water. And so we get some rain happening in that area. All right, next one is a warm front. These form where warm air moves towards cold air. In this case, it is the warm air that's being the bully. Cold air is just kind of over here, minding its business, and the warm air moves in this way and is forced to rise up on top of the cold air. And again, as it does that, you do get this sort of line of clouds here. Now, this tends to be a little bit of a more mild type of thing. This is not as severe. You don't get the really severe thunderstorms. This tends to be kind of drizzly, overcast, cloudy, gray kind of weather when you get this. I will remind you one more time that these are called storm fronts, so they are all stormy weather. It's just kind of how stormy it is. It's the difference between a really severe thunderstorm and just some kind of mildly gray, drizzly weather. All right, so notice that this idea that the front is moving this way. Notice that this is the symbol for our warm front, and you can see that the little half circles actually go on in the direction that it's moving. And so in this case, you have the warm air moving up this way and being forced to rise up on top of the cold air here. And there again is your symbol for a warm front. In this case, the warm air would be moving in that direction. This is basically what a warm front is going to look like. Again, you can kind of see the difference here. You can see that line there. Okay, occluded fronts. Occluded fronts are a little bit tricky here. This actually involves 3 air masses, not just 2. Basically, the idea here is that you get one cold air mass here that's moving along very quickly. You get another cold air mass here that's basically kind of stalled out and is staying still. And you have a warm air mass right here in between them. And so an occluded front happens when this cold air mass catches up with this cold air mass and kind of pinches off the warm air mass and makes it kind of float on top of both of them. Okay, now think about this. You have cold air pushing on warm air, pushing on cold air. And remember, your symbol for a cold front was these little triangles here. Your symbol for a warm front was the little circles. So it kind of makes sense that the symbol for an occluded front is a mixture of those two, the triangles and the circles. So, and we would say that this is the point of occlusion right here. This is the idea where this cold front, this cold air mass, has kind of caught up with this cold air mass here and has created and forced this warm air to rise up on top of them. All right, last one is a stationary front. This is when a cold front and a warm front cannot really overtake each other. This is basically a tie. Okay, so in these situations, what you get is that these 2 air masses kind of stop moving across the country and they just sit there. And if you happen to be right here, if this is Virginia in this area right here, then you get some kind of bad weather for several days in a row because these air masses really aren't moving. They're kind of stuck in that place. Eventually they'll start moving again, but for a while you're going to be stuck with some rainy, cloudy weather for several days. All right. Now, at this point, you guys should know that when cold air and warm air come together, there's a difference in pressure. And the high pressure air, the cold high pressure air, is going to want to move towards the warm low pressure air. But you should also know that it's not quite that simple as sort of a straight line moving from one place to another. So what we have is the Coriolis effect, which makes things kind of swirl around. Now, I'm going to show you a little video clip here because I think this is a really good way, this is a really good example of showing how this works. This is a video that I got off of YouTube, and this is a guy that's using sort of a program here to show you how that air is going to move around. So as you're watching that video, there will be some things written on the screen and things like that, and you'll see exactly what you have to write down in your notes. This is in the video section of your notes page. Okay, so go ahead and watch this little video clip and fill in what you need to fill in on your notes page.
All right, so pressure system circulation. When we look at a low pressure system or a high pressure system, the way the wind circulates changes for each, and it's important to understand each so we could better predict the weather and learn how this weather is going to come towards us, or whether we're going to have some cooler air, maybe some warmer air from the south. If there was, right here in the map, we see a low pressure system in the Great Plains area. We know if that is an L, that represents the lowest pressure. So around that low, there would be higher pressure at different places around this low. If that low represents the lowest pressure, obviously these places would be higher. We know that air moves from high to low, so that the air is going to move in towards this low, but we can't forget about our friend the Coriolis. In towards that low, it's going to curve to the right. So the air is being pushed that way from high pressure to low pressure, but we know that it's not actually going to move that way. It's going to curve to the right. So the air will move this way, to the right. High to low, but curves to the right. High to low, but curves to the right. Some people still have an issue with the high to low pressure wind there, and they're saying, hey, that arrow's not curving to the right. That arrow's, remember, we're talking about moving in the direction of the wind. So if I put this upside down, we see that as the air moves from the high to the low, it curves to the right. So that is curving to the right, although it doesn't necessarily look like it is curving to the right. The air is going to be moving in towards the low, and it sets up circulation that is counterclockwise. If we look, the air has a counterclockwise circulation. So here's a map of the United States, and we have a low pressure sitting in the middle of the United States. And if that's low pressure around, and if everybody in the United States blew a couple bubbles, we would see that the air would move from the higher pressure towards low, right? Air moves from high to low. Well, there's a low in the middle, higher pressure around it. Air is going to move in towards the low. And this is what it would look like if the Earth wasn't. The Earth is spinning. We're going to get these bubbles are going to curve. And they set up a circulation that is counterclockwise. So in a low pressure system, the circulation of the wind is counterclockwise and in towards the low. Counterclockwise, head on back to our notes, we see that the circulation in a low pressure system is air moves into a low and air circulates counterclockwise in a low. From here, we could then easily assume that the opposite is going to be true for high pressure. Pressure there in the center. The air is going to want to move from high to a lower pressure at different places around that high. If that's lower pressure here, the air is going to move from high to the lower pressure. But instead of going straight from high, we know that it's going to curve to the right. That air is going to curve to the right. High to low, but curves to the right. High to low, but curves to the right. High to low, but curves to the right. And now we have, instead of air moving in, We have air that's moving away from a high, out of a high, different clockwise. We see a different circulation. We see clockwise circulation. So in a high pressure system, the air is moving out of the high and the air is circulating clockwise in a high. So it's the exact opposite of what we saw of the low. And we see the same thing, our bubble map, that we now see that the winds are circulating clockwise, and we see that those bubbles are moving away or out of the high pressure. So air moves into a low, but out of a high. And let's put two of them together. There's our high pressure, and we see the air moves out of the high, but into the low. It moves clockwise around the high pressure, counterclockwise around the low pressure. This is not something you need to necessarily memorize, because you could just go back and look at your map. You could draw an H and know that the air moves towards, since it's in the northern hemisphere, is going to curve to the right. Now, if you're a little advanced, you say, well, wait a second, what if I was in the southern hemisphere? And that's true. If you're in the southern hemisphere, things are going to go a little bit different. If there's a low pressure there, here we have the wind moving into counterclockwise. But if we move to the southern hemisphere, here we are in Argentina, we see that in a low pressure system, it's moving clockwise. That's because the Coriolis effect is opposite in the southern hemisphere. In the southern hemisphere, we get a curve to the left. So here we have this as a cyclone, which really means it's a storm. Low pressure, loser weather. It brings stormy, cloudy weather. Well, it's not going to stay stormy and cloudy right there around Nebraska all the time. That low pressure is going to move. And when they move across the United States, they generally move from the west towards low pressure comes towards our area. So we see we're coming towards the Great Lakes. We're right just below Lake Ontario. You'll notice that when the low pressure is to our west, the air comes from the south into our area. It brings warm air up from the south when the low pressure is there, moves over our area and comes to the other side. Now you'll see where the bubbles are coming from. They're coming from Quebec and Ontario. The colder Canadian air is now coming across the Great Lakes into our area, and that's also what sets up things like lake effect snow. So where this low is and across the United States is very important in forecasting weather. These storms, and remember that storm is a low pressure system, also known as a cyclone, a low pressure system. They generally move across the United States from the southwest towards the northeast. And if we take a look at where we are right here, you'll notice that these lows generally move into our area from the southwest. So if we know that a low is moving towards a low pressure system that's here, we know that it's probably going to be moving towards our area in this way. So if we see a low pressure off to the southwest, we know that that low pressure might be bringing our weather towards us in the future. This sets up these storm tracks come from what we studied before, the Coriolis effect. All right, remember we looked at this part. This was on page 14 of your reference tables. If we were to put the United States where we are between 30 and 60 degrees north, hang Florida down just a little bit more there, winds are blowing. The planetary winds caused by the Coriolis effect generally move like this. And look at how that matches up so well right there. If we zoom in, we see that the planetary winds, these are the things that push or blow that low pressure system from southwest towards northeast. So that low pressure starting there and then moving across the United States in that direction is caused by these planetary winds that we see on page 14 of the reference tables. So storm movement or tracks, low pressure systems move across the Earth based on these planetary winds. You can use page 14 in your reference tables. It'll really help you out with a lot of the questions.
All right, well, there you have it, air masses and storm fronts. So, started off by talking about air masses. We have maritime air masses, which are wet, continental is dry, polar is cold, and tropical is hot. Those are the main ones. There's also the Arctic one, which is sort of extra cold, but those are the main four right there. Remember, we can have kind of any combination of those where you could have, say, cold and dry, or you could have hot and wet, any sort of combination of those, depending on where the air mass is coming from. And then when those air masses meet up with each other, you get a storm front. That is the boundary between air masses. And this is caused by differences in air pressure. The cold, high pressure, sinking air is going to get underneath the warm, rising, low pressure air and force that air to rise. When the warm, wet air rises, the water starts to condense and form clouds and rain. So we have cold fronts where the cold air is the one pushing around the warm air. We have warm fronts. Those tend to be a little bit milder, and it is the warm air that's kind of pushing the cold air and rising up on top of it. We have stationary fronts, which stick around for a long time. They're stationary, meaning not moving. And we have occluded fronts, which include three air masses, which is basically, it's like kind of a sandwich with the warm air in the middle and the cold air masses on both sides of it. And we have pressure system circulations, which is what you saw in that video clip. You have high pressure moving towards low pressure, accompanied by the Coriolis effect, which makes things circulate in clockwise directions in the northern hemisphere, or curve to the right in the northern hemisphere and curve to the left in the southern hemisphere. And we will learn more about this in class, and I will see you then.